in PDEs. And here I will talk about something that is somehow strange. I was surprised in many conferences, people never heard about this, and they were surprised that I was able to play with some easy tricks and functions to get some somehow interesting results sometimes. Maybe the others should judge the type of results we got, but I will mention soon what does it mean for P functions. And then I will show you a bunch of applications in several directions because we can use them in many directions. Of course, maximum principle is the strongest tool to find estimates usually, or to prove uniqueness theorem in a partial differential equation. But here I will talk about maximum principle for what we call P functions and the way to use it in directions. In several directions in the elliptic case, in several directions in the parabolic case. Maybe I have a lot of information on these slides. I will try to focus on what is more important. I was thinking yesterday, shall I put more? Finally, I realized I already have 40 slides. So I just want to give a flavor. And I also realized that maybe one day is not good to write maybe a monography on this topic because from some point of view is known, but from my point of view, I know, for instance, Yao, the famous Fields medalist, he knew about this secret kind of tools. And he found kind of interesting results, but on manifolds. So here I will also mention quickly what is happening in the parabolic case. And then I will talk about, I was interested very recently on studying Monge-Ampère. So I had some previous results in the previous years. But then I was invited to give some course in a summer course in Italy. And some Italian colleagues suggested me to work. They like this kind of P functions, and we had some recent contributions. So there are 2 papers this year, 2021. So that's why I will focus at the end on my results on Monge-Ampère. I will mention other results here, but this is the idea. So now let me start with the origin. Here we have some all kinds of formulas. They are very easy to deal with, but maybe I will jump to the visual image of what I mentioned here because it is easier to see. I just realized that I cannot write here directly. So we all know in Calculus 1, in our calculus courses, that if you have a concave up function and you have, let's say, a critical point, of course, you have a minimum for that function in that interval AB. But we never talk about the fact that if, of course, there it is important locally what is happening. So you have the critical point, and if f is positive at that point, that this is local minimum. But you never talk about the full picture. Like I have an interval AB, f second is positive. So either we have something like this or something like this. But in both situations, it is clear maximum where the maximum occurs. Forget about local minimum. The maximum occurs at the endpoints of the interval, of the given interval. So in this case, it occurs here. In this case, it occurs here at A, here at B, here at A. So this is somehow the origin of the maximum principle. And in the same way, we can discuss about minimum principle. I will mention it. On top of that, we can notice that at this point, if I consider the tangent line, the slope of the tangent line is positive, right? So in other words, fx by fx, I mean derivative from right, from left here in this case, from the left of B is positive. Here you can say that the slope is negative, but I can think in a different direction because I want to visualize and understand in higher dimension what is happening. So here I live in the interval AB, and outer direction means in the positive side of x-axis, outer direction at B. Outer direction at A means in the opposite direction. So here at A, I'm interested in the derivative with respect to minus x with the opposite direction. So if the slope is negative, but this means the slope of the tangent line. So this means fx is negative, f derivative with minus x will be positive. So this means that at the point, for sure, if I have f second positive, the maximum occurs at the endpoints, unless the function is constant. Of course, if it is constant, the straight maximum can occur everywhere, and that's it. But at the point of maximum, the outer derivative is positive. And the same happened for the minimum. If you have f second negative on an interval AB, the minimum occurs at the endpoints. Either in this picture here, it is obvious in this picture here. And those points, the outer derivative, somehow I call it outer derivative, is negative. In this case. So this is what we call somehow maximum minimum principle in one dimension. And this is what I mentioned here. It is very clear we can extend this one to more general. If you have f plus a of x prime plus b of fx, and with this b negative, all this information, all these results are still valid. So now it was very natural to see what is happening in higher dimension. So in the higher dimension, the first step is to replace f second with the Laplacian. So then Hoff proved that if the Laplacian is positive in a bounded domain, the maximum of u is attained on the boundary, unless u is constant. And the same Hoff proved later that at the point of maximum, the normal derivative, the derivative in the normal direction to the boundary, or not necessarily in the normal, in an exterior outward direction, a direction which has the angle maximum 90 degrees with the normal direction, is always positive. And then Nirenberg extended this first maximum principle to parabolic. This is like parabolic inequalities. Of course, the parabolic equation appears in heat diffusion or any other kind of diffusion problems. And the maximum, when you have parabolic problems, when u depends also on t, the maximum of u is attained either on the boundary of omega or at the initial time t. And then Friedman extended this so-called second maximum principle of Hoff, or people working on PDEs, they call it Hoff lemma. So he extended Hoff lemma to parabolic problems. Again, here for parabolic problems, the maximum is on the boundary of omega at the initial time. But if it is on the boundary of omega, once again, the normal derivative is positive. And of course, we can extend this to more general, not only to Laplacian of u is greater than 0, less than 0, this maximum principle. We can extend it to this kind of second order linear differential operators. Here, when I repeat indexes, I mean I have summation. I did not write summation. Ij goes from 1 to n of aij, uij. Uij derivative with respect to xi, xj, plus some coefficient derivative, first order derivatives, plus coefficient u. And we can extend even to more linear. So these are the maximum principles. So standard maximum principle, standard theory, we touch it sometimes in our PDE courses. But what is amazing is that in the 70s, Larry Payne from Cornell, I even have here, if somebody is interested, unfortunately he passed away, he was very old, I think 85 when he passed away. The AMS and Cyan, they dedicated some article to Larry Payne, who has a very interesting life. He was working in a shop store. He was very working guy, cleaning or doing a good job. And when the war came, the owner did not even want to leave him to go to the war. But then in the army, they discovered that he's a very smart guy and he got education. And then finally, he's a famous guy. He built the applied math department in Cornell. And then he got still prize or in PDs, he has a lot of contribution. We can check on that. And he has very nice idea, very natural and very nice idea. And he was so modest sometimes that I always found, I had the chance to meet him. I always found what it was already easy to be done. But this is not true because, as I said, he had a very good feeling of what is happening behind many models, and then he put this in all this idea in some differential equation, and he obtained very nice results. So we call them P functions. P function means nothing else than a good combination of the solution and their derivatives, and how to develop maximum principle for this and how to use them in a useful direction. So we call them P function because Payne was the one who used in the 70s, and then I rediscovered later these ones, and I obtained some results in this direction. So for simplicity, let's look at what is happening, let's say, with the torsion problem. This is a model for many other equations, but let's choose one of the easiest PDEs. Delta U is -1. In omega, U is 0 on the boundary. If you look at the one-dimensional case, let's say omega is the interval 0, 1. We notice that this function u of x is x times 1 over x minus 2 is the solution of the problem. If you compute the second derivative, you get -1. And of course, on the boundary at 0 and at 1, you get 0. And now if you take this combination, u prime square plus 2u, you see it is constant. So this is very important. Now in the n-dimensional case, if you consider the ball, we have radial solution. We know that solution of this problem in the ball is of this type, 1 minus magnitude of x to the power 2 over 2n. If you compute Laplacian, you get -1. On the boundary, of course, if norm of x is 1, then you get 0. So if you take this combination, is again constant. So now Payne was thinking, why not to consider this kind of combination, gradient plus a constant u, on general domains and see when do they have maximum or minimum principal for appropriate values of alpha. So the type of maximum principal we can find for this kind of combination are of this type. You have a combination of x, u, du, or first order derivative, second order derivatives, and try to show that they satisfy the maximum on the boundary, the maximum at some critical points when omega is convex. Maybe I will explain later why, or minimum value on the boundary when the, let's say, the solution have convex level sets. So these are the 3 types of maximum principles that are known in the literature. And the idea is I can now invent many kind of functions, but important is to have something useful, to use something. And let me give some model problem. For instance, for the torsion problem, I have here delta u is -2 is 0 on the boundary. If you take this combination, Miranda, this combination, and this was somehow the first result on P function. We did not call them P function at that time, but Miranda noticed that if you take this combination, the maximum is obtained on the boundary. Now, using some computations in normal coordinates with respect to the boundary, you fix at the point of the boundary, you consider a system of coordinates given by the normal direction and the direction which gives the principal curvature. You can rewrite what does this maximum principle says and find some estimates on the gradient in terms of the k-min is the minimum of the curvature of the boundary of omega. So not only on the gradient, which appears always when you want to measure all kind of energies, this is the torsion problem, maybe this appears when you want to measure the torsional rigidity, but also on u. So maximum of u, look at the graph of u. In other words, it's like you have a mountain. This is the graph. You can guess how far is the top up based on what you measure at the base of the mountain, based on what you measure here on the boundary omega, on the curvature. And moreover, these inequalities are what we call isoperimetric inequalities. So the equality happens when you have beautiful shapes. So here you have equality if and only if the domain is a ball. And I will show soon why this is true. So another example is the first frequency of a fixed membrane. Delta u plus lambda 1, u is 0, u is 0. So we have a discrete spectrum. I consider only the first eigenvalue, first eigenfunction. If you take this combination, we can show that it takes maximum where u takes maximum. And working with this inequality, we are able to prove that lambda 1 is greater than pi squared over 4 rho square, where rho is the radius of the largest ball you can inscribe in omega. And here the equality holds for a strip, for an infinite strip. So these are a kind of model problems, and one application is in the sense of isoperimetric inequalities, because these isoperimetric inequalities are related to shape optimization. Usually we want to optimize energies, and you see that those energies are optimized for certain shape, or you get some inequalities. When the inequalities, what are the best inequalities? And the best inequalities are the so-called isoperimetric inequalities, because you get equality when some beautiful shape happens. So a second famous result in PDEs is this result of Basile Guidas, Wei Mei Ni, and Louis Nirenberg in '79. It is a very important result. Here I talk only about the ball. They prove it in a more general context. It is very interesting that here F, the only condition on F was to be Lipschitz. And his result was amazing because it says the following. If you have a domain symmetric with respect to, let's say, a hyperplane, then the solution of the problem is also symmetric. U here is U here is U here. And in particular, if you have a ball, the solution is radial. So U along radius is the same along some circles. So he proved this one using maximum principle and nice idea of mathematician Alexandrov on a moving plane method. Very nice, elegant proof to show that the solution is radial. Later on, this guy Aviles proved that in fact we can show in this particular case if f has a certain sign that is radial symmetric using a certain p function for Laplacian of u. So among other results in this paper, I extended this to what we call K-Hessian equation. Unfortunately, I don't think I mentioned what does it mean K-Hessian, and I don't think I can write. So if you take the Hessian of a function, so you take all the second order derivatives and you consider the eigenvalue of the Hessian, lambda 1, lambda 2, lambda n, and you take elementary symmetric function of the eigenvalue, sum when 1 is less than I1, less than I2, less than up to In, of product of the type lambda I1, lambda I2, up to lambda Ik, then this Sk is this kind of sum. So in particular, when k is 1 means sum of the eigenvalue, lambda 1 plus lambda 2 plus lambda 3 plus lambda n. And if lambda 1, lambda 2, lambda 3 are the eigenvalues of the Hessian, this means the Laplacian. When k is n, you get the determinant. You get lambda 1 times lambda 2 times lambda n, the value of the Hessian. So when you take the determinant, this Sn will be the determinant, so it will be the determinant of the Hessian. And there are some intermediate cases, so I prove the same. And this is the p function you take. This is the p function you take. You can show that for the ball, this is 0 on the boundary. And using maximum principle, you can show that it is 0 everywhere. And this relation tells you somehow that always the gradient is perpendicular on the tangential direction somehow. And you have a ball. This happens for the ball. So that's how you prove that the solution is not. So this is happening for the ball, but the fact that the solution is radial is equivalent to the fact that this one is 0. And that's it. So another important thing is the shape of the free boundaries. So the free boundaries are studied by many people. There are standard examples. Imagine that you have an ice in a glass of water, and there is the free boundary is the shape between the ice and the water. So in many contexts, free boundaries appears, even in financial math or in many other fields. But now it is important to know what is the PDE modeling that equation and what is the condition that appear on the free boundary. So now this problem, as I said, it is a model for the torsion problems, but it can be considered a model for many things. And Serin was interested, he was in Minnesota, and he was interested in a problem in fluid mechanics. So the fluid passing through a pipe, the question was, what should be the cross section of the pipe such that the tangential stress is constant along the walls of the pipe? And this condition is written in this way. Gradient should be constant on the boundary of omega. What omega is the cross section of the pipe. In terms of torsional rigidity, you have an elastic bar, and the cross section of the bar is omega, and you want to optimize the torsional rigidity. So the torsional rigidity is optimal if on the boundary you have gradient of u is constant. And this is also another some kind of result. These two are famous, this Gidas Nirenberg, because for the first time, this result tells you that the geometry of the environment is reflected in the geometry of the solution. So it doesn't matter the model you have in some environment, the geometry of the environment has impact on the geometry of the solution. And in fact, in this case, the solution inherits the whole geometry of the region. So then people, then they were interested to see if the symmetry is broken when we have symmetry breaking in some situation, or for which kind of model, let's say that the geometry of the environment still is preserved by the geometry of the solution. And here, as I said, this kind of problem has solution if and only if the omega is a ball and the solution is radial, and we can find the solution explicitly here. But now here, if you look at this one, is interesting. I think Weinberger was the reviewer of the paper, because in the same journal, the subsequent paper is on the same problem. And here, Serin used what Gildas Nirenberg used, the moving plane method and maximum principles. But Weinberger used a function. So he played with this combination. He showed that it takes maximum on the boundary unless it is constant. And then he used a relic type identity to show that P is identically constant. And P identically constant, if you look at the Laplacian, you see that the second derivative are third order derivatives are 0. And in some way, you get that the Hessian coincide with the identity is a multiple of the identity. So the function is radial, and then the solution, the omega is above. If the function is radial, U is 0 on the boundary, means that the omega is above. And these were the spherical shape. And then if you look on MathSciNet, in both cases, there are hundreds, if not thousands of papers related to this one. And then the same in this situation. And I was curious about characterizing ellipsoidal shapes. And I was surprised to discover at that time there were only 3 results, and all of them in 2 dimensions, and all of them about Laplacian. So about this torsion problem, delta U is -1, U is 0, but with a different overdetermination. We call this one overdetermination. So Payne proved that if the overdetermination is that on the boundary you can measure that x-axis gradient is constant, then for sure you are in an ellipse. Here I said ellipsoid, but yeah, in higher dimension you are in an ellipsoid. And he played with this P function, x-axis gradient to U minus to U. Then Arrow and Philippin work on the same problem, but they replace the overdetermination with this one. Curvature of the boundary times the gradient at power 3 is constant on the boundary of omega. So this will force again the domain to be an ellipse. You cannot have solution unless the domain is an ellipse. And then Aneda and Poru consider same kind of overdetermination, not for Laplacian here, but the equation was replaced by determinant of D2U is 1. And again, it was in 2 dimensions. And they show it is, you have solution if you have the domain is an ellipse. And the result of Poru and Aneda was extended by these guys in 2014 to higher dimension. Now what we did, here I mentioned only Laplacian, but we wrote a paper with very basic short proofs, fully characterizing free ellipsoidal shapes in terms of this kind of overdetermined problems. And we consider Rn, not only R2, and fully general nonlinear operator here of elliptic types. So I mentioned the Laplacian because I work with the Laplacian. So one of them is this one, and I will tell you shortly what this condition says. So let me show you in the picture here. This says that if you have any kind of phenomena which is modeled by a second order differential equation of this type, second order derivatives, combination of them is constant inside omega, but the combination should be somehow elliptic. So the operator you have here, you should be elliptic. Laplacian is one case, but you have any kind of crazy operators, constant. And let's say U is 0 on the boundary. And then we consider omega lambda to be a kind of zoom of omega. So let's say omega lambda is the set of all lambda x with x in omega, and lambda is something between 0 and 1. Such that omega lambda stays inside the omega, because if I make a larger zoom, maybe some piece of omega lambda will go out. No, I need this condition to be inside. And if I know that U is alpha on the boundary of omega lambda, then we have ellipsoid. This is the first result. And this is somehow amazing because this means that any models which is given by a second order partial differential equation this type, if the solution has 2 homothetic level sets, then the environment should be ellipsoid. You cannot have solutions otherwise. So the only way to have solution is to have quadratic functions in an ellipsoid. So this is the first result. And based on this one, we extended the result to fully nonlinear differential operator with this condition. And then also under this condition, again, we get ellipsoid. Under this condition, we get again ellipsoid, where G is the Gauss curvature of the boundary. H is the support function, means the distance from the origin to the tangent plane to, so the support function at some point X on the boundary is the distance from the origin to the tangent plane to that point on the boundary. So for the sake of showing some proofs, I copy-pasted the proof from the paper. So it was half a page proof for this result. And since I copy-pasted, imagine here you have capital F, any kind of differential operator. So we choose these two functions. V1 is u minus alpha, V2 is lambda square u minus alpha. If you compute the Laplacian of V1, you get Laplacian of u minus bye-bye. Here alpha disappears if you compute Laplacian because it's constant. So Laplacian of V1, let's imagine F is Laplacian, but you can think at any second order derivative. If you take any second order derivative of V1, you get the same second order derivative for u plus 0 because this is bye-bye. If you compute here second order derivative, when you differentiate once, this one goes out. You see, differentiate again, this one goes out. So by also this constant. So you remain then with Laplacian of V2 is the same as Laplacian of u in omega lambda. So imagine F is the Laplacian. So both satisfy Laplacian of VEC. And on the boundary, since on the boundary of omega lambda, since u was alpha, if you remember, u is alpha, alpha minus alpha, of course, is 0. And here we have a rescaling for V2. So V2 at some point here is u here, at 0. V2 at some point here is u on the boundary of omega, which is 0. So both satisfy the same equation. Then by uniqueness, they are equal. I differentiate 2 times with respect to xi and xj. So I get that uijx is the same as uij lambda minus 1x. So this gives me an iteration. So in other words, I can say that uij of x is the same as uij of lambda nx for any x. And now since lambda is between 0 and 1, when I pass to the limit, I get here 0 inside. So in other words, all the second derivative of u with respect to x, everywhere in omega lambda, give me the same value, this constant, uij is 0. So if the second, all the second order derivatives are constant, then the solution is a quadratic polynomial. And what does it mean u is alpha on the boundary? So you have a quadratic surface enclosing something, omega lambda. So it is an ellipsoid. And if omega lambda is ellipsoid, of course, this is homothetic with omega, omega will be ellipsoid. And that's it. So this is one way to characterize ellipsoidal shape. Later on here, I have some scary stuff about anisotropic equation. I won't enter in details, but the idea is that you can build all kind. I build the most general possible kind of anisotropic operator, and we consider this kind of equation Q plus Q is 0, where Q is, as I said, a very scary operator. And the motivation comes from 2 directions. From what I understood, this kind of equation appears a lot in physical field related to some well-established model of surface energy in metallurgy, crystallography, especially, or crystalline fracture theory, especially in these 2 fields. But there's also geometric meeting because in some particular case, when I choose this one, let's say G of capital G to be this one and P to be 2, I get what is called Finsler Laplacian. And this is something that appears in Finsler geometry, with kind of Minkowski geometry. So it seems there are a lot of interest for this kind of operator in both physics and geometry. So then I was thinking to study them and look at free boundaries. So now how to characterize the free boundaries for us? Everything is built based on this F. F is a kind of norm. And imagine that F is a kind of norm. And we define the wolf shape something like this, the set of all x such that somehow this kind of norm is R. This is a wolf shape. So now the problem is, what is the shape of free boundary in some anisotropic free boundary problem? Is the shape of a free boundary a wolf shape? And I gave several with a colleague from Constanza, my hometown on the border of Black Sea, where is the largest port of Black Sea. So with Luminița, Barbu, we proved several results in the very general context. We extended Serine result to this anisotropic kind of equation. Here we consider some domains with some holes, and we saw that this is possible when you have a wolf-shaped ring. And here, what's happening if you have many holes? We treated these kind of problems. So now maybe it was better to draw, but if you are curious, wolf shapes depending on the norm, I'm sure there should be many kind of pictures on the. So you have many examples of wolf shapes depending on how you choose that F. This is what you mean by wolf shape. It's a kind of ball in a certain norm somehow. So this is about free boundary, the shape of free boundaries. Next, convexity result. This is also, I found this paper amazing by this Russian mathematician in a Russian channel. I love this kind of paper saying something really deep in just half a page or something like this. The whole paper maybe is a page and a half. But he opened the door to many important things, to some convexity results. So in his paper, proved uniqueness of the critical point, but if you read carefully the paper, you realize that in fact his paper says more than this. So for the torsion problem here, this one, delta U is -1, U is 0. If the domain is convex, so let's say delta U is -1, the graph is something like this, right? So he said that all the level set, if you take cross section with horizontal plane, you get curves which are convex. This is his result. And maybe it sounds like, and what is this? It is convex. It's very important because in many applications it's important, including this field of study. So to derive minimum principles, I need sometimes upper estimate on the second order derivatives. And maybe some people do not feel any relation, but the fact that I have convexity of level sets helped me to find upper estimate for the second order derivative of the solution. So as I said, this was amazing and very elegant proof. So I will tell you shortly the proof. He considered this weird function at first view, very strange function. But if you look at this one, you see that this one along level curves of the function u is exactly curvature of the level curve, gradient of power 3 plus 2u determinant of d2u. So now what is strange, when he computed the Laplacian of this one, you get something which is negative. So then we have minimum principle. So as I said, few lines the proofs, you get minimum principle. So this minimum is obtained on the boundary, but when you look at the boundary, u is 0 on the boundary. So by this term, and since omega is convex, the curvature here is not negative. The gradient is positive. So we know that on the boundary, m is positive, and the minimum is obtained on the boundary. So then this m is positive everywhere. But when you look at this one, take this function v root of u, you see that the Laplacian of v is this one, and the determinant of d2v is exactly this quantity, this special function. And we already proved that this m is positive, so the determinant is positive, Laplacian is negative. So in 2 dimensions, this means the trace of the Hessian, this is the Laplacian, is negative. The determinant so the trace, this means if you look at the eigenvalue, sum of eigenvalues is negative, product of eigenvalue is positive. So this means the matrix is negative. So this means that v equals square root of u is strictly concave. And that's it, very elegant. And then Acker, Payne, and Philippin extended this to the first eigenfunction of the Laplacian. And then recently, Ma, Shi, and Yi, these Chinese have a lot of results in this direction. So they were able to extend this result in higher dimension. Imagine to compute the Laplacian of this monster in higher dimension. Like you have n+1 lines and columns in the determinant. Even if you want to develop this determinant, you get a monster. And imagine that you compute the Laplacian and they were able to prove that it's less or equal than 0. So normally the idea is simple, but you have to have a lot of patience to do the computation and succeed to get what you want, playing with estimates and other things. So these are about convexity results. The time is we start 12:45 there and we finish after 40-50 minutes, right? Yes. So I think I have to hurry a little bit. So this kind of results were extended by few guys, again using maximum principle. So for instance, Caffarelli, Friedman here use maximum principle for the determinant of d2 of the Hessian of this function. So this is the function he chose, and he proved the maximum principle for this one. And anyway, other people did other things. now for Liouville, you know the famous result of Liouville, that if you have a harmonic function everywhere, which is bounded, then it should be constant. So then harmonic function means delta u is 0. Delta u is 0 means the PDE. So then people in PDEs were thinking, why not to understand, because there is also a physical meaning in some contexts. What does it mean that the function, the solution, the only solution of some PDEs are the constant solutions? So so Liouville result, in other words, was that if u is constant and delta u is 0 everywhere in Rn, then if it is bounded and delta u is 0 everywhere, then u is constant. So then I discovered this jewel. I was really shocked when I discovered this jewel, because nobody quoted this one, and it was related to this kind of P functions. So Modica proved this journal that if you have a bounded function of which is solution of this equation, and let's say the antiderivative of f has this property, there is a point x naught such that antiderivative of this f of x naught is 0, then u is constant. And the proof is based on maximum principle for this kind of nice combination I use. So that's why I was excited, because I knew how to extend the things. And I was working and discovered there is difficulty at some point. And then on Scholar Google, I discovered that Caffarelli, Garofalo, Segala already proved it in 94. So they extended this one. And after many years recently, now MathSciNet updated the information. And on MathSciNet, you can see that this one is quoted by many people, because recently a lot of people work on extension of this kind of results. But they work with this kind of combination. Be careful, this one. So then I was thinking, why not to try to work with other combination? And I started first in Rn, because I discovered that Cuckoo-McCoy proved some results working with other functions. And then I said, why not to work for the P Laplacian with this kind of function, and show that if you have a nonlinearity for the P plus equation, we satisfy this condition, and beta is something like this, then the only solution of these problems, only bounded solution of these problems, are the constant solutions. So you cannot have other bounded solutions. So this is a Liouville type theorem. And then based on this one, why to work with what these guys did here, this kind of combination, I try to work with some good quotients, and we extended with Luminenza Barbu to anisotropic here, and something very, very general here. Now, quickly, you understood what we did for linear, for elliptic case, but it is a very natural idea, and pay notice this, that we can consider the same for parabolic problems. So in parabolic problems, you had heat diffusion, and you want to see how the diffusion behave on time. So then why not to try to work with the P function you consider in the elliptic case and multiply it with exponential function depending on t. And then, of course, you have to rearrange because things do not work, but he succeeded to discover that this one satisfies the maximum principle. So in other words, he found some explicit decay bounds for the solution, for the gradient, and for this kind of integral in terms of the initial condition on U, in terms of this H. Based on maximum principle, this is what we consider usually in an elliptic case, but you multiply it with this one, and when you say that this is smaller than the same on the boundary, or the same here, it is an initial time. This is the same as the initial time. The same is, it is something prescribed, this H times e to the 0. So then you move this exponential on the other side, and you get that all function are smaller than some quantity which depends on the initial condition to the minus. So you get some explicit decay bounds in time. And of course, you are in the kitchen. I was in the kitchen. You cook something. In the kitchen, we use cylindrical things. You hit on the bottom, and you are making a soup or something. So why not to understand what is happening in this kind of situation? So here there is a model problem where I discuss decay estimates with respect to the spatial direction. Like I have a vertical cylinder, it is kept at temperature 0 laterally and on the top, and then we have some heat on the bottom. So of course there is some heat diffusion. So we want to see explicitly how the heat diffusion behaves. And I have this paper result of this type working with this kind of exponential here. So of course, when you use the maximum principle, you will get that it's smaller than something. And then when you move this on the other side, you get a bound which is something prescribed, this h e to the minus beta x3. So you know how it decreases along x3 axis. So you have explicit decay bounds. So now regarding Monge-Ampere equation, I had an interest on this based on constant Gauss curvature. If you look at the surface as a graph of a function, x plus 1 is u of x1, x2, xn, then the Gauss curvature is given in this way. So what does it mean, constant Gauss curvature? That this one is constant, right? So in other words, this kind of surfaces can be characterized in terms of Monge-Ampere equation. And there are some natural questions here. So imagine you have a constant Gauss curvature surface with a boundary down in a plane. And you measure the angle between the surface and the plane of the boundary. If this angle is constant, how does it look the surface? And we show that it is a hemisphere. What are the optimal and lower and upper bounds on the height of the constant Gauss curvature? So on the top, can you measure the top based on what you have at the base of the mountain? And then among all constant Gauss, this is an isoperimetric inequality. Among all constant Gauss curvature of given area and boundary in a plane, which one enclosed like this is the plane? This is the, maybe it's not a good example because a chocolate. So this is the plane. You have a constant Gauss curvature above this plane with the boundary in the plane. Among all of them of given area, we can enclose the largest volume with plane of the boundary. And we proved here that it is the hemisphere. And then what can we say about the existence of constant Gauss curvature surfaces making a contact angle with some vertical walls? So you have some vertical walls, you have a surface, but the boundary is on the wall, and you can measure the angle between the surface and the vertical wall. So if you know the angle, you have what we call constant angle boundary condition. These are very hard to study, and that's why there are no results. So anyway, I prove all the things in these two papers. I gave precise answer in this paper in 2 dimensions. Here, what was surprising is that a minimum principle occurs, and it was easier to find more things. I was not able to find minimum principle, and finally I published only a paper with maximum principle in higher dimension. And the P function I consider are this one. So if you have this Monge-Ampere equation, you have these crazy functions here, and they are very suitable for what I need. And we get optimal bounds, isoperimetric inequalities, everything we want somehow. I won't enter in this, but this was the interest few years ago, so this appears in 2014. And there are few results on maximum principle in particular cases. If you want to see the proof, I will skip the proof. I have here the proofs. And even this is the proof for the, so here I prove that if you have constant angle between the surface and the plane of the boundary, then you have a hemisphere. Next here, for instance, there was only one result in the literature by this guy who is an expert in constant mean curvature equation, who found some bounds on the U mean, but very easy bounds. Like he found only from one side, if I remember, that it's less or equal than 1 over root of k naught. But not only that we improved the bounds, we got something better, but we got also on the other side the bound. And these bounds are not any kind of bounds. They are isoperimetric, the best ones. We call them the best one, the optimal ones. You have equality here if and only if the boundary of if omega is a disk, and so the surface is a hemisphere. And this equality is the one I told you about, related to the volume and the area. So this tells you, in other words, that among all constant Gauss curvature of given area, the one which has the large volume is the hemisphere. In fact, always you have inequality, but the equality happens if you have a hemisphere. So you keep area fixed, and the volume reach the maximum when you have equality. And this happens when you have a hemisphere. And then, as I told you, if you consider this is the model for constant Gauss curvature surfaces. If you have Dirichlet boundary condition, the existence is known. You have Newman boundary condition, the existence is known. You have Robin boundary condition, things are known. But for contact angle boundary condition, nothing is known. So these are like also some kind of big knives. Maybe you recognize some fields medalists. So somehow this topic is not easy to prove existence. I was not into that direction. I was lucky enough to use this P function to discover some other things related to this. And what I proved here, I proved the necessary condition of solvability. So this kind of problem, we have this necessary condition of solvability for this problem. And this is the condition that if the curvature, the Gauss curvature of the surface is constant, is K naught, then this relation should happen between K naught, the angle made with the vertical walls, and these are the minimum and the maximum of the curvature of the boundary. So this condition should happen for such problems. And these conditions are optimal. So equality happens when you have a spherical surface. So that's it. These are the previous one. And now let me talk about some reasons. This looks very ugly, but with Giovanni Poru and Monica Maras, we are thinking to have a feature. So if you remember well here, Weinberger. So I said this was somehow the first ones were here. So for this one, we have this P function, and for this one, Weinberger played with this one. So normally, when you have Laplacian, it's natural to work with the gradient of U square. But you have fully nonlinear. I was lucky enough for Monge-Ampere. I just mentioned that I had this kind of strange combinations. These ones where only the gradient appear and do, and these are really optimal. It was a big surprise for me because I expected to have P function. The best ones are the ones where you have second order derivatives. But still, it seems there is a difference. These ones are the best one when you find isoperimetric inequalities where the optimal shape is spherical. And the second derivatives appears when you have optimal shapes which are ellipsoidal. So now we are thinking to see what is happening here and to play with very general P functions. So, sorry. So this is what I said, the K Hessian equation. In this paper, we mentioned we work on K Hessian equation, but I will mention only what we got for Monge-Ampere. So to build this kind of Newton tensor, so you start with T naught is the identity matrix, and then you build this based on this iteration. So T2 will be what? Sigma 1 I minus T naught, which is the identity, times the Hessian, and so on and so on. You build a Newton tensor, whose elements we can prove that are exactly the derivative with respect to J of this elementary symmetric function. And then we build this kind of P function, this or this. And the natural question is, do these functions attain maximum or minimum value on the boundary? So now, in 2 dimensions, we prove in this paper that when f is non-decreasing, when k is n is equal to, so when we have Monge-Ampere, the determinant of d to u equal f of u, and we have this term here in the P function, then for sure we have maximum on the boundary. And then we extended this one to higher dimension, and some applications, I can tell you some application. H is, I denote by HK if you have a surface like the boundary of omega. The surface has some principal curvatures. So let's say I have n minus 1 or n principal curvature. HK means elementary symmetric sum of the principal curvatures. So H1 means the sum of the curvatures, and this makes you think of the mean curvature. Hn is the product, so this immediately tells you that you have Gauss curvature there, and then you have intermediate. So what is interesting here, this is very atypical. First time maybe you see in the literature this kind of overdetermination. that if you have something like this quotient of the curvature times the gradient of this power is this one on the boundary, then for sure you have a ball. Or in the case k equal n, if f is 1 and we have this condition on the boundary, these conditions I can express it in terms of the Gauss curvature. I did not mention. So we have this term here, but when this nu is n, I have Tn minus ij uij, nothing else than the Gauss curvature by the gradient of u at power n plus 1. If this is constant on the boundary, then in 2D you have ellipse, and in n dimension we have ellipsoid. So that's it shortly. Thanks a lot. And thanks a lot, Dr. Kyriakos, for this nice invitation.
We thank you a lot, Dr. Christian, for your very, very interesting talk. And it was enjoyable, very enjoyable to watch. Are there any questions to address to Dr. Christian Enache?
Yes.
So can I ask, I mean, first of all, thank you very much. It was really nice. The first question is, if there is a way, how do you construct these P functions? I mean,
yeah, this is as I said, I was lucky somehow that people are surprised. Somehow I rediscovered that pain work some time ago. And you know, we are lucky sometimes when we have our own way to work in this direction.
Yeah, of course.
I wanted to change. I'm interested in another thing. I think it's good to do other things. And maybe next time I like this, I have some results on frequencies on membranes and plates and relation with music and other things. But maybe this is the next time if Dr. Kyriakos in the future wants to. But the idea comes very easy. So you want to get isoperimetric inequalities, right?
Right. Right.
You want to get optimal things. So optimal things, maybe you want to get them in the ball. So then you look at what is happening in the ball. That's why I mentioned here.
Oh, right. Okay. Okay.
So you look at the ball. In the ball, you have this kind of solution. And you see that in the ball, this is constant.
Right.
So you try to find those combinations which are constant in a certain shape. Beautiful shape.
Right.
So on the ball, I know that this is constant. And the same I did here. If you want, maybe let me see if I find the paper. In this paper with the one we had now this year, let me see if I find it somewhere. I will show you quickly because I mentioned Field theorem. But what we did, we tried to understand these K Hessian equations in general. So what we did was to analyze first what is happening in the ball, even though the computations look ugly and maybe you see a lot of tensors and so on. So I mentioned here the story that in the case delta E equal 1, people build this kind, had this idea, Payne had this idea.
Right.
And then I started with, anyway, I introduced here, the radial case. What is happening in the case of a ball? In the case of a ball, we know that the solution is radial. Right. And we know that we build this kind of function, and we notice not only that it is constant on the ball, but you see that if f is non-decreasing, this function phi, the combination I choose, is derivative is positive, so it is increasing. So I know for sure that in the case of the ball, this one takes maximum on the boundary, right?
Right.
Or when f is non-increasing, this is derivative is negative. So for sure, when f is non-increasing, the minimum should be on the boundary in the case of a ball. But now it's not so, the idea is trivial, but the computations are horrible and it's not so obvious in general what is happening. If you have a general domain, is this still true? And this is the natural idea. So many times you look at what is happening in the ball, and even in PDEs, sometimes you look at properties in the ball and you try to understand if the same happens in general perturbation of the ball, or like convex domains, do they still preserve those properties?
Right.
This is the idea.
Okay.
Yeah.
I'll ask a second question and let somebody else. The second question is, because there is this a close relationship between harmonicity of a function and holomorphicity, right, of the components. Yeah. Have you ever thought about exploring possibilities in the case of several complex variables, right?
Yeah, I know. I never tried, and as I said, I was thinking at one moment even to leave aside this. I know that there are still things. There are many things that can be done. I can write papers on parabolic problems maybe easily, but I want to focus on other things. And I know that for maximum principle, I was very happy to obtain that one characterizing constant Gauss curvature surfaces, because those results tell you something. But now it is good to have also students. For instance, here we don't have PhD programs. It is different to work with students.
Of course.
Yeah. So maybe this is another, of course, always there are many directions. I know that there are people working on this Monge-Ampère, also complex Monge-Ampère equations.
Right.
And from some point of view, is not to advertise myself. I know nothing about optimal transportation, but I know that there are fields medalists working on Figalli.
Villani started.
Villani, yeah, they are working on optimal transformation. And optimal transformations, there you will see that Monge-Ampères appear. So
of course.
Interesting. Unfortunately, I think I should send them my papers because nobody read my papers. So it seems they are very unknown somehow.
Okay, so make it two, mine too. So I know exactly how you feel.
No, nobody read them. I'm sure about this. So once I gave a talk and people were surprised, what is this? Because they're like, some proofs were so elementary, and yeah, they didn't know that you can play with this kind of nice combination to get some results.
Dr. Christian, you have to join ResearchGate. I think you don't have a ResearchGate profile, and this will solve the problems.
No, I have ResearchGate, but as I said, yeah, unfortunately, even for eigenvalues, what is strange, I wanted to give a talk. There are isoperimetric inequalities for frequencies of membranes, and it is amazing that you have frequencies. There was something almost 100 years ago for the first one, but then things were not known. For the second frequency of a free membrane, the result was proved 1 or 2 years ago in Acta Mathematica. So it's not like they are easy to state, but hard to prove. And for higher order, nothing is known. And with numerical method, you can see now that maybe the optimal shapes are not the ball. So maybe there is no way to choose pure math, to use pure math to find what is the optimal shape. But I have several results on higher order. So nothing is known for higher order. I have several results on higher order eigenvalues when the domain has some rotational symmetry. So when I have some rotational symmetry, we prove that the ball is still the one which optimizes the eigenvalues. But as I said, I think they are not really, I don't know if people read them, maybe some reviewers sometimes. And
no, but I think isometric problems are always seen and looked at in mathematics, right? Because I mean,
or maybe it is hard to prove this kind of isoperimetric.
It's very hard. There are some recent results by, well, there is an Israeli guy, right? Famous Millman of the Millman clan, but a son, not Vitali, Emanuel Millman, in which they prove isoperimetric inequality symmetric measure spaces with Ricci curvature bounds and convexity properties of the corresponding functions. But also this Monge-Ampère, I mean, they appear everywhere. So whatever you come up with, I think will be useful to some people.
Yeah, maybe I should post it more often on the internet, because as I said, I am the only one quoting my papers. I don't think there is somebody else.
Any other question to Dr. Christian?
May I say something?
Yes.
Okay. First of all, thank you very much for this presentation. It's very impressive, Christian. Regarding this multidimensional case that you mentioned, and together with Dr. Kalogeropoulos, I mean that if once I mentioned there is a Kruglikov brackets, this is now maybe someone already heard about it. If I'm not wrong, it is exactly about multidimensional cases for some kind of optimization problems that you solve. And if I'm not wrong, they use more complicated domains, not balls, but in different kind of manifolds. And this is pure geometric approach. If I'm not wrong, I showed once the paper to you. And of course, it's very like, you have to study this. It's complicated, but it's another way to approach this kind of problems.
To tell you the truth, I don't remember this one if you have sent it, but to
I
tell
have
you
a
the
paper,
truth, I'm
yes, I
very,
have
maybe
paper.
some people will take it in a negative way. I like very easy things. So I'm a very easygoing and I like easy, and I was lucky to use easy tools to prove things. So there are also, I was lucky enough from my point of view, probably because I got used to this kind of things. I feel that I don't use heavy guns like for Dr. Nicholas isoperimetric inequalities. In my results, I proved them in 2 dimensions, and the idea was the same. You know what is happening in the disk, and then I use conformal transplantation of what is happening in the disk to prove my results. This was the idea used by Zeg in some cases, and it is somehow a very elegant way to prove isoperimetric inequality sometimes.
And one more thing, a kind of advertisement, maybe. I just saw when you were talking, you published a paper in results of in math.
Yes.
Results in math in February. A note on Monge-Ampère equation in R2.
Yeah, this one. Yes, yes.
Yes. So can you send it to me if just?
Yeah, I will send it if you I don't know if
because
you
I don't have access to.
Yeah, okay,
right?
okay, I
I
understand.
tried to download using that website.
You can see it, I can show you now. This is really baby style, like grandmother style, doing computations like babies. So you will be surprised maybe. But in the other paper, things are more difficult maybe. Let me show you, and you'll see that this is really baby style, but the surprise was to see that that all kind of miracles happened and terms disappeared, and that's it. This is the one.
Mm.
So if you see, we do baby style. We just differentiate to become, look, 1, 1, 1. This means derivative with respect to x1, then with respect to x2, with respect to x2. We compute all the time, and then some miracles happen. Some terms disappear, and then you get what you want. This was
But
yeah, I understand. Yeah.
That's very interesting because you choose a very good function.
Yeah, this is I choose the good function.
Miracles happen and terms disappear, and you can get the result. That's the point.
Yeah, this is the point. So as I said, normally it's not a big deal. There is no, but there are people who publish this kind of papers even in Invenciones or Communication, some Chinese group, but they had horrible computations behind them. But normally the idea is very easy. You want a maximum principal, you have to build a differential inequality, like Laplacian is greater than 0, or if not Laplacian, some second order derivative, but first order greater than 0. And try to get it. And here, as I said, the math is so surprising sometimes that I found the right function, and then do all kinds of horrible computation, and terms disappear, and you get what you want. It is surprising. Surprising, yes.
Oh, okay, thank you.
Thank you.
Can I ask Dr. Arman, what was this bracket that you called? I have never heard the name. If you please repeat it, if you don't mind.
Kruglikov, Russian name, Kruglikov.
Kruglikov with a K. Kruglikov.
With K, R, U.
Right.
J, L, I, K, O, V. Kruglikov.
Okay, all right. And regarding Professor Enache's statement, regarding that you are working with very easy things and so on, I have heard this comment from some of the greatest mathematicians that I have ever met. Miss Agromov was telling me the same thing. This is totally simple. This is totally naive. Of course, 40 years later, nobody has been able to improve any of these proofs. But so I think you are in good company. Allow me to say that.
This is a very nice discussion.
Let's stay on the earth with this kind of statement. But anyway, it was a pleasure. Sorry.
Just so you say, I guess you post on the archive these papers, right?
No, I never posted on archive.
You should.
But by the way, to make a parenthesis, I was surprised that there are some Russians now quoting the ones on eigenvalues, and somebody even published in Advances in Math something. But they are doing, Russian school. They are doing very heavy.
So be careful. If Russians start to work on this topic, you should be careful.
Yeah.
what they
Yeah.
do.
Yeah, but
But
this
anyways,
topic of maximum
just one more
principle
remark,
for,
because
yeah.
I know that most of people, they don't read Russian journals. I mean, good journals like mathematical заметки, this mathematical notes.
No, this, as I said, there are
Scornic
some,
mathematics.
yeah.
There are many good papers there.
Of course.
There are jewels, and as I said, I found this kind of jewels, like amazing results proved in 1 page or 2 pages. This is something that I like a lot, to tell you the truth. If I see a 100 pages paper with a lot of complicated things, I'm usually discouraged, especially now when we are involved in so many things. We don't have the passion sometimes to read all this crazy computation in detail. This is a problem somehow. If you are a researcher doing only research in a place, maybe it's different. But it is a pleasure, as I said, that paper of Makalimanov opened the door to a lot of nice researches in the area of convexity of PDEs, and that paper was really amazing. So he played with that function, he built that function, and normally in half a page, he proved an amazing results in that Russian, but it was in Russian. So people discovered it later when it was translated in English, I think. So I think there are some Russian journals where the papers were later translated after a few years or something.
Yeah, also in theoretical physics, there are stuff like that.
I see.
The Russians discovered it maybe 10 years earlier than the others, and then they translated just to English, just translation. That's the point.
Yes. And there are many results. I don't know, maybe for Armen it might look impolite, but the talk was, I did not even think of this. But for instance, people do not know. In my thesis, at one moment I wrote about this, that in fact, the German school call it off maximum principle. But in fact, there are other Russians who prove it in the same times or little earlier, the same maximum principles. So the Russian schools proved the same in the same time period. So at that time, people did not have internet, email, they did not know about. And you know, there are famous stories, you know, even the story of John Nash. He was obsessed with the idea of proving a problem of Hilbert on the regularity of solution of PDEs. And when he wrote the results, I think he sent it to, if I'm not wrong, to American Journal of Math, or I don't remember now. But anyway, he was thinking that based on that results, he will deserve the Fields Medal. He was also a little bit proud of his results. And then some people think that maybe this crazy news was the starting point of having some health issues. I don't know. He was extremely disappointed to discover that the result was already proved by the Giorgi in some journal in Italy. But at that time, people were disconnected. They did not know. So one day he discovered that the same result was proved. The proofs are different. So that's why in PDEs, people discuss about the Giorgi proof or Nash-Moser proof. But yeah, so he discovered that the Giorgi was, in fact, the first, not him. And he was very disappointed. And he decided, I think he submitted to Acta Mathematica, and the reviewers or the ones who took care of the paper were Fields medalists, Bombieri and Hormander. And they did not find this polite that he decided to withdraw the paper. He was furious, and then he submitted to American Journal of Math to get a certain prize at least, something like this. It sounds crazy, but I read there is a monography on John Nash, and there is this story there. They used that monography to make that movie, A Beautiful Mind.
Do you remember the title?
One small question, may I? Maybe it is a stupid question.
Mr. Armen, if I can just say that in 4 minutes, some people will have to teach. We can continue this discussion. I would like to thank.
Sorry, I have to leave, but thank you very much.
Yeah, no problem. We can meet one day.
Continue this discussion definitely. Inshallah, when there is no corona, we will invite you to give a talk in our colloquium seminar here, Dr. Christian.
No, as I said, I will be honored because I have this, you know, I was in Kuwait. Kuwait means something to me. And I know you are building now, you have amazing campus, maybe the best campus in the world or something like this. Right. So in the future, I will be happy to, yeah.
in Saturday.
See-
Yeah, definitely.
Thank you.
Thank you very much, and we will continue this discussion. Definitely. Thank you very much
Yeah.
for the talk and for the questions.
Yeah, thank you.
Thank you.
Thank you.
See you. See you. See you.
Have a good day, everyone.
Greetings to
See you.
Sharjah. Greetings to
Thank
Sharjah.
you. Thank you.
Ciao to everybody.
Ciao.
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 Ciao to Milano.